Finding
Yeah,
me.
of course. Of course.
Great. Thanks. Um, yeah, so why I tend to get very excited about things. And so getting into complexity science, I tend to, be like, this is the philosophy to rule all philosophies and sort of life. So I see it not just as a field of science, but really as like a philosophy of life and also of contemplation. Um, so some of the main points that the reason why I see that is let me there's a lot of counterintuitive behavior that happens when we start thinking about the world in this linear causal fashion, right? So the rough perspective, I guess, let me just share a few simple slides. Uh, It'll help me to round a little bit. So one of the sort of insights is if we think of the world in this reductionist material way and we think of linear causal chains, we think that A causes B causes C, and this is how we reason about the world. We tend to run into problems when we start to deal with real world things. As long as we stay in the lab, we're okay. If we have like one atom or two atoms or five atoms, right? But when we deal with a complex system, we really sort of lose that uh, reasoning capacity or predictive capacity, right? So things like this happen. So LA Highway 405 was known as one of the worst congested highways in the US, and they spent a few billion dollars increasing it, adding a few lanes. So it was a multi-year construction project, lots of money spent, and after all was said and done, the average speed dropped from 25, 28 down to 19 miles per hour and the travel time increased from 23 minutes to 34 minutes. So all that money invested kind of backfired into worse traffic, right? Basically, in retrospect, people are like, oh yeah, making space for more drivers only encouraged more people to drive. So feedback loops, right? Feedback loops that we can't really predict ahead of time. And so all this sort of scientific thinking about like, okay, here's the parts, here's how they interact, therefore I now understand the system, tends to be wrong. One sort of way to think about it is if we think of a causal chain, for example, we want to reduce forest fires. So if we have an open flame, that causes a forest fire, right? So, okay, if that's our model of the world, then, people cause open flames. Therefore, we need to invest money into telling people not to burn fires, right? So we have Smokey the Bear, all kinds of rules and laws, right? And then we're like, okay, we solved forest fires, right? But, when you look at the real world, it's like somehow this doesn't solve forest fires. Why would that be, right? And you're like, oh, well, people aren't the only thing causing open flames, right? There are other causes for this, right? And in fact, lightning or hot sun, and when there is dry underbrush, that can cause a lot of forest fires. But open flame can actually reduce the amount of dry underbrush. So maybe instead, what we should do is invest money into burning away the dry underbrush. So they have these controlled burn projects where you set the forest on fire intentionally to reduce dry underbrush in a controlled way, right? Okay, great. We solved forest fires, right? And again, right, as long as we keep adding little pieces to this network, we can do this forever. We'll never see the whole picture. So we can think of like, okay, well, why is forest fire a problem? Actually, it's because, it causes risk to humans, it causes CO2 emissions, air quality, risk to plants and animals, erosion soil, right? And so maybe those are the things we should deal with, not the fire itself, right? Dry underbrush also helps, or reducing dry underbrush, uh, creates more risk to plants and animals, erodes soil. Uh, CO2 emission makes the hot sun stronger, which creates more open flames and more dry underbrush, right? So maybe instead we should invest money into carbon capture, right? And now the network is getting quite complicated. And if we remember sort of meta perspective, right? We started with a very simple network and we were like, okay, this is the causal chain. Now we thought for another 3 minutes and we have this chain, right? How certain are we that we have the full picture now, right? So the idea is that the network is probably a lot more complex and we'll probably never get there. So perhaps this whole project of trying to come up with more causes and more connections is just not the way to go, right? So this brings this sort of contemplative don't know mind, which in Buddhism is very practiced and welcomed, right? And there's perhaps some other way in which we can run our life rather than finding these simple causal chains. So complex systems is sort of one of the counters to that. It's basically a system with many interacting components, no defining symmetries, many distinct parts, interactable. So something from big atomic nuclei, uranium atom, things like that, to DNA strands, different types of organisms from bacteria to animals, societies, traffic networks, economies. So all the things we deal with in the real world are basically complex systems. And the key concepts we deal with here are emergence, self-organization, phase transitions, but also that humility of don't know mind, that even though, yeah, we have these tools, we're always remembering that we don't know anything. And the beauty of complex systems is that, where spiritual philosophy will always often derive from um, kind of a different perspective, complex system science is derived from reductionist material science, right? So you start precisely with, normal science and you get into this holistic perspective just by trying to apply it to real world systems. So at this point, I think I'll stop with the slides and yeah, and see if we want to go into some discussion. So yeah, how do you guys um, see or understand complex systems, or what? Maybe if you have specific questions already, or yeah.
Oh, but I have a question.
Mhm.
Um, can you give a sense, either your perspective or what you think is a kind of semi-agreed upon understanding of complexity science as an umbrella for what?
As
So
an
I don't mean phenomena. I don't
mhm,
mean about complex systems. I get
mhm,
that, sort of.
mhm,
I mean, complexity science does not entail X and Y and does entail A and B. Is there a
mhm,
way of don't not about don't talk about for just for my like
mhm,
help me,
mhm.
not the phenomenon, not the object of study, but the means by which it's conceptualized. Can you help me understand a little bit?
I see. So not what is complex system versus not complex system. That's not the
Yeah,
question.
like yeah, I think there's like I kind of get that, and there's a lot of writing about that, but
Mhm,
that isn't complex. But complexity science is
mhm.
about the science, presumably.
Yeah, yeah,
And I candidly, I like pretend to sort of work in this area, but
yeah.
I'm not sure I fully understand actually. It's
Mhm,
not totally clear to me what are the boundaries
mhm,
um, in terms of, I don't know if it's models or if
mhm,
it's epistemology or ontology. I'm not sure. Maybe, I don't know, maybe others here have a greater clarity. I've sort of latched on to sort of dynamical systems sorts of
mhm,
ideas,
mhm,
but I have the sense
mhm,
that like I'm sort of I'm a part of there's other boats around me and I don't realize
mhm,
that there are and
mhm, mhm.
kind of sort of
Yeah, yeah.
perspective. And do you have any thoughts on that?
Yeah, yeah. So I think the way I understand your question is sort of what are the tools that complexity science uses? Dynamical systems being sort of one of the tools, one of the methods, but maybe there are other ones, right, to study complex systems,
Sure. If you, if
right?
yeah, if I think is that the way you see it? Do you think it's essentially made up of essentially tools? You see them as functionally similar?
Yeah. Yeah, I guess the way I see it is that there is the object of study, the complex systems, right?
Sure.
Which is
Sure.
um, I like to just to mention one thing. I like to distinguish it as there are simple systems, there are complicated systems,
Ah.
and there are complex systems,
Yep.
right? And complex and
Yep.
complicated are almost like opposite things, right?
Opposite.
So
Yep.
a
Yep. Yep.
car is complicated, but it's not complex because everything is following very direct engineered causal chains, right? This electrical signal causes this thing, which causes this component to move, which, right? And if anything in that causal chain misfires, the car doesn't work, right? Whereas a complex system is like an ecology. If an organism dies, the ecology does not stop functioning, right? Like it's highly redundant, it's self-organized, it's emergent, right?
Yep.
And so
Yep. Yep.
humans can
Got that.
understand complicated systems, but we can't understand complex systems somehow fundamentally, right? So what complexity science is trying to do, it's a science that's being like, okay, given a complex system, we know we can't understand it. Is there anything we can do? Right? Should we just give up and not look at them and only look at atoms in vacuum chambers? Or, can we try? Right? And it's kind of like anything goes, right? There's lots of people trying lots of different things and failing a lot and sometimes succeeding a little, right?
Uh-huh.
Yeah. And so
Uh-huh.
I think to a large extent it's this approach of like, okay, let's try to do good science of this thing that really we can't study with the understanding that we can't fully understand it. And then, sometimes some methods emerge that are like, well, this is giving us some ground. At least it's interesting, right? So dynamical systems theory is one big piece of this, which the way I
Uh-huh.
see it is it's kind of study of differential equations and systems of differential equations and how they um, get set up. And then
Okay.
that's dynamical systems theory.
Okay.
The like things like phase transition or universality or renormalization group, like that whole space is another tool, right? Where you basically say that, oh, look, there is a disjoint bunch of atoms and molecules floating around as a gas, and now we cool them down, and their interatomic, intermolecular bonds all of a sudden coalesce it into a completely different sort of thing. It goes from a gas to a liquid, right? And in
Uh-huh.
physics, we
Uh-huh.
know exactly how that works. We have all the equations, right? And then it goes to a solid, right? And again, we know
Uh-huh.
exactly how that works. But now we have a bunch of people running around and doing their own individual thing, and all of a sudden they coalesce into a cohesive society, right? It seems reminiscent, but it's also not exactly the same. So, can we use this math of phase transition to show this? Or for a traffic jam, right? Traffic jams are modeled as phase transitions. So it's a different set of sort of mathematics, right, than dynamical systems. There's a few other things. Network science is another one, right? Um, and once you start listing them, there's quite a lot. We can actually something maybe just to pull up the glossary because that was kind of one thought I had is to have this on screen while talking about this because this gives um, a nice way to kind of maybe guide the discussion because there's a lot of terms in complexity science that really sort of address your question, Amit, about, what are the different things that are used there, game theory, things like that.
I guess the thing that I'm still struggling with is I kind of wonder whether you would have scientists who say that all science is complexity science to some degree.
Hmm, hmm,
Um, and I don't know if that is a not a true statement,
hmm, hmm,
a partially true statement, or a true statement.
hmm,
Um, but I'm sort of left. I think it's important. And
hmm,
the other thing I'm sort of hoping, curious if others or your thoughts on this or others is um, what kind of crosstalk is there between these different what you're describing as complexity science tools? Do you
hmm,
think there's importance for crosstalk? Do you think it is sufficient, for example,
hmm,
to try to study complex systems through dynamical systems? Do you think there's a loss? Do you think that there's something missing there?
hmm, hmm.
Um, I
Yeah.
don't know if you or others can speak to that.
Yeah,
The,
I'm
maybe.
the,
curious.
I could also say something I have. I usually I don't use the word complexity science when I describe my own work.
Hmm,
Interesting, but uh,
Right.
but I'm aware of the concepts that are listed here.
Yeah.
And so the one observation that I can actually make is that uh, very often we admire the way how physicists do things. And so it is amazing to see that there is sort of a theory in physics that then predicts the mass of the electron or so, and then it can be measured and it agrees to like 10 decimal places or something like this. So we find this very, very impressive. And my whole life I spent to develop mathematics in biology. And usually it's not like that. So we might have, for example, a description of the HIV virus, we might have a description of cancer, but it is not that at the end of the day we have a prediction and now in the lab you can measure something and you can say whether the theory is right or wrong by many decimal places. It's not like that.
Mhm.
And why is it not like that? Because the most complicated system that physicists study is infinitely simpler than what the simplest organism in biology actually is. So there is somehow an irreducible complexity in the world of biology that we are confronted with. And you could call this is a need for complexity science. You could say sort of one cell is much more complicated than a star. Physicists, have a hard time to really describe a star like the sun in great detail, but they can describe a lot about it. Planets are even harder. But a cell, this is already much, much more complicated. And so here is where the method of physics, however great it is, doesn't really map over in the same way. And this is kind of the embarrassment. And therefore, I think there is something to this idea of irreducible complexity. And yet, we have to make progress by trying to. So, my own strategy would always be to try to find a simple way to think about it and hope that we get somewhere in that way. I think this is one way to deal with complexity science. So, to ask what's the simplest possible thing I can propose that might describe aspects of the system that is the beginning, and then others can elaborate on that. I heard physicists, for example, talking in Princeton at the Institute of Advanced Study. They were asking themselves, will we ever reach a time in science when biology will be understood as well as physics is understood?
Mm.
And they said, yes, we will reach this point, and then it will be called physics.
Uh, yeah. To me, one of the like AI is a really powerful new tool for complexity science, in some sense, because in a way, right, we can't write down these very simple differential equations with like, three terms to describe protein folding, right? But apparently we can have a neural network, AlphaFold, was developed by DeepMind, which predicts protein folding basically as accurately as we need, supposedly. Although maybe not quite. But um, so in some sense, maybe we're coming up on a new paradigm of doing science altogether, where instead of trying to come up with a simple equation that we can write down on a line or on a piece of paper, right? The fundamental like atom of the tool that we're using will be some neural networks that are trained as, right? So instead of mathematical equations, we'll have neural networks. But right, I think trading that off is a thing. Um, Also, I guess to your question of, is it enough to just use dynamical systems theory to study? Is like, well, if you're trying to understand a phase transition from, traffic jam to like probably not enough, right? There is a lot of stuff you can say using dynamical systems theory, but there's other aspects that, right? It's like using math to describe something versus using a neural network to describe something. They'll capture
Mm.
different understandings. They have their strengths and weaknesses. So
Have
people
you ever
definitely.
seen yeah, are you familiar with is there anybody has anyone mapped this almost like the kind of
Mm,
um, overlap between these various tools with
mm,
respect to
mm,
the
mm.
dimensions of phenomena they do or don't account for? I haven't. I kind
No.
of assume maybe you can ask Neil. Maybe he's done something like that or thought about that. I think I'm asking just for totally like the most practical, concrete purposes. Um, yeah.
Mhm.
I just want to ask you one other thing. So in the way you're talking, both of you are talking, what's the difference in your mind between, say, just like systems science and complexity science? I'm not sure I fully understand the distinction actually.
But I use neither of those. So there is the Institute for Systems
Yeah,
Analysis, YASA, for example, in Vienna. I was a postdoc there, like
yeah,
30
yeah,
complexity state system science. I don't use that precisely for the questions that you are asking, actually. So
Mhm.
for me, there would be like tools to do something. So I talk about stochastic processes, about differential equations, then there are certain questions and so on.
yeah,
I also don't like data science. Data
Mhm.
science is a big deal these days.
yeah.
So, but that doesn't mean that the activity is not interesting. So, but
Mhm.
so
Right.
these big categories are,
Mhm.
I don't know how to understand them. So, for example, dynamical systems. When you say dynamical systems, in our department, there's a guy who got the Fields Medal in dynamical systems, Kurt McDonald. He's one of the
Yeah,
greatest mathematicians. And so,
yeah.
what he does has nothing to do with I've ever done in my life.
It's fascinating. Yeah,
So this is
yeah.
real dynamical system. Sort of this has
Right,
to do
right.
with maps on complex functions or so. And if I read his papers, then the one thing that I ever saw was like billiard balls on polygon-shaped billiard tables